Lano, could you please share I would like to share my screen. Okay.
Okay, sir.
Okay. Today we will review numerical methods using in astrophysical simulation. First of all, please note that some images and other materials in this slide retained by the original authors. They are intended for IFSC use only. Okay. For doing numerical simulation, numerical simulation provides qualitative and quantitative scientific prediction by means of mathematical modeling, numerical methods, and the third is software tools. Some of you may be familiar with solver or software. For example, MESA is very popular in Department of Astronomy in ITB, but it is only one of the means to doing simulation. The first thing that you have to know that how the universe work is come to single conclusion that is we need to understand hydrodynamics, let me write this H letter, and the second is mechanics, orbital mechanics. These are two equations that are really important to understand how the universe works. I intended this lecture to deliver a review for undergraduate students, but I hope that those who are intend in this lecture will refresh the understanding of numerical methods. And the main components of numerical simulation design cycles are as follows. First are the human being. The second is scientific knowledge. This is a mathematical expression. The third is software, computer codes. computer hardware and the human being for inspecting and interpreting the simulation result. Some of you may recognize this website. This is astrophysical source code library. So you can search many codes dealing with astrophysical modeling or simulation. In business process perspective, these are some of steps that we are doing. First is a problem statement. What is the astrophysical phenomena? What is the objective of your research? Do we need to compute integral quantities, or we only see a snapshot of field data at a specific time, or do we want to improve performance of a simulation code, for example? But the second is also important. What is the mathematical model? What is the initial boundary value problems? We have the boundary value problems, but we also have to think that the boundary value problem may change by time. And also initial conditions. And of course, the most important is partial differential equation. This is the real problems in astrophysical simulation. Not only ordinary differential equation, but we come to a kind of differential equation, partial differential equation. What is the reference frame? Are we doing in Cartesian frame or spherical? Are there symmetries? Are we doing in 1 dimension or 2 dimension or 3 dimension? Are there terms that are do we need to neglect the terms with no or little influence? Now, the main business of numerical methods we are discussing today is about discretization. The foundation I apologize. I cannot share my screen. Please help. Please help me.
Sorry, sir, can you share screen again? Please try.
Okay. Okay. This is our main discussion today. It is about discretization. So we would like to discuss grid-based methods. We would like to talk about finite difference, for short, I write this FD or FDM. And another is finite volume method. Or FGM for short. If we are doing grade-based method, we have to be familiar with the concept of mesh, how to generate the mesh. Is the mesh was a structure or block structure or unstructured? How do we generate the mesh? We can use some of tools or software, for example, GMSH, or using scientific Python, so package spatial, Mayavi, for example, or many tools relating to computational geometry software. What is the mesh size? Do we have to adapting mesh refinement? Do we have to adapting mesh size or the geometry of mesh? The second discussion today is also mesh-free discretization, but we are only discuss the smooth particle hydrodynamics, or SPH for short. Last but not least is about time discretization. We have to make a local time stepping. Is there do we need to adapting time step control? These are examples about structure mesh. If you look very close to this mesh, in every node, okay, we are frequently using keywords node. Node for a spatial node. There is also a temporal node relating to time or spatial, 1 dimension, 2 dimension, or 3D. Sorry. These are example of 2 dimension structure uniform. We call this structure uniform because if you look at one of the internal nodes, here, there are 4 incidents come to this node. 1, 2, 3, 4. You have to look at every internal nodes, spatial internal nodes. This is the uniform one. This is the form structure mesh. This is another example. Perturb. This is a block structure. For all this example, all inner nodes have the same number of its incident element. It is 4. Second example is about unstructured mesh. Some of inner nodes here, internal nodes, have different degrees. If you look here, for example, 1, 2, 3, 4, okay, 6. Yeah, I think we have 6 here, 6 incident elements. Count to these internal spatial nodes, but here we could inspect. There are some internal nodes which have 7 or 8 incident elements. So we call this two example are unstructured mesh. And this is the last example. We know that this is a structure, but for figure B, this is unstructured, and for figure C, this side is structure, but this face is unstructured. So we call this, we may say this mesh structure was semi-structured mesh. Yeah, I will introduce this some of mesh generator, for example, GMSA, and it's have been 20 years development, and now it is delivered to a smartphone. So it becomes more intuitive. This is one of example. This is tools for preparing boundary condition in simulation, including in astrophysical simulation. This is another development. Okay. The next step of numerical simulation process is iterative solver. We have to solve the algebraic system, which is very large, millions of unknown. You can see here that for 2 dimensions, for example, we would have many internal nodes, which becomes to many unknowns. And it's the building blocks of big algebraic system. So we are doing matrix operation, which is very large. So we need to know how to solve linear subproblems, these subproblems, using iterative methods, for example, Gauss-Seidel. The next step is implementation and debugging, choosing programming language. the six-step simulation run. If you are very familiar with some of code or software in ASCL.NET, some of us indeed doing parameterization, but in principle, we have to know what we are doing, what is working in the software, the simulation code. So many processes in this numerical simulation, and it is impossible doing this simulation without collaboration. You can see in this Mesa Star homepage, Mesa version 1 authors. This is Bill Paxton, if you know. Okay. Now, let's discuss about finite difference method. You know that the first derivative of a function f in calculus could be expressed by limit delta x tends to 0 and or for finite delta x, first derivative of f at x approximated by this expression. And we have the remainder terms, which in the order of h or delta x. Now we have to do discretization. By applying delta x was xi plus 1 minus x minus xi. This is a very simple example of how we use the mesh. We use one dimension mesh. This is node I. On the right was node I plus 1. On the left is node I minus 1. I'll skip this slide, graphical representation. It's very easy to understand. And the second was, and the second is backward difference. It's similar as forward difference, except that we change delta x with minus delta x. So if you look at the formalization of Taylor series, we understand how this finite difference method built by expanding the value of function f near x at node I plus 1, and we approximate, and this infinite series into finite series. For better approximation, we can do a central difference approximation of the first derivative. So we have a better order of remainder in delta x squared. This is an example for this method, finite difference method, for velocity of rockets given by this function, and we want to calculate the acceleration, which is one kind of ordinary differential equation at time t equals 16 seconds, using a step size of 2 seconds. So we approximate the acceleration by this expression in central difference. Using delta t equal 2 and t I plus 1 equals 18, t I minus 1 equal 14. We have this expression for these values. As we know, the exact value of the acceleration, because the velocity function is a kind of analytic function, we could compute or calculate the absolute relative true error. We have very small error, less than 0.5%. This table compare the using of 3 types of difference approximation: FDD or forward difference, forward divided difference, backward, and central difference. And what about higher derivatives? It is just the same. We use the expansion of the Taylor series here, and we have to deal with 2 internal nodes around I here, I plus 1, I plus 2, for example, and we subtract to equation here, Then we have an approximation, second order derivatives, function f at internal node I relating to other internal nodes one step ahead from I and two steps ahead from node I. And now we use central difference in order to achieve higher order accuracy. We can use this approximation related to relative to node I. We calculate, or we need the value at left node from one step backward from I and one step forward from node I. Now we use the same example for another application, which is jerk or sudden movement. Which is the second derivative of the velocity. With the same time step size, 2 seconds. So we calculate acceleration here. And we come to very small absolute relative true error. This epsilon is bigger if we are using lower order accuracy. Now we come to real problems in astrophysical simulation. That is partial differential equation. As I mentioned before, that fundamental equation to describe the working of the universe was first hydrodynamics, and the second orbital mechanics. Let's focus on this hydrodynamics for this lecture. For orbital mechanics, Pak Budi may give lecture about numerical methods in n-body problems. Hydrodynamics may incorporate with viscosity, and we come to an equation called Navier-Stokes. Equation, or it would be incorporated with magnetic field so this is MHD, magnetohydrodynamics, or it would be incorporated with radiation transfer, and we call this radiation hydrodynamics. If you would like to read some numerical methods applying in engineering, these terms sometimes called advection. So I hope you are very familiar with these terms, this terminology. You are very familiar with this ordinary differential equation. I hope this is an example of ODE for short, which have only one independent variables. But for PDE, partial differential equation, it have more than one independent variables. This is subject to certain conditions. We have independent variable U and dependent variable X and Y. This is an example of description of models, real problems, physical problems dealing with ordinary differential equations. It depends only on one variable, t, time. Theta here is temperature, I think. This is another real problems in the same situation, in the same environment, but we have here 4 variables: spatial variable, spherical geometry, and time. Now, most of partial differential equation are in the second order linear PDEs. So we can write the general PDEs for many of simulation problem or physical simulation, astrophysical simulation in this form: A times partial derivatives of variable U to X or to Y, or a combination of X and Y, plus another terms here, D, as a function of X, Y, U, and first partial derivatives of u to x or to y. It can be elliptic, parabolic, or hyperbolic. If you remember, if you are astronomy student or you are familiar with conic section concept of eccentricity, there are many range of eccentricity. E less than 0, for example, E equals 0, or E greater than 0. E for eccentricity. We use the same category here, elliptic, parabolic, hyperbolic, in the same order here. How do you know it? These come from this value, b squared minus 4ac. So it is very clear, if this value less than 0, then the equation is elliptic. This is an example. The second derivative, a partial derivative of temperature, for example, to x and to y here. So we have a equal 1, b equal 0, c equal 1. So this value is less than 0. The next is parabolic PDE. This value is 0. For example, this is an example of heat equation. A equal K, B equal 0, C equal 0. So this value is 0. So this equation is parabolic PDE. The third is hyperbolic. You may be very familiar with this equation related to wave solution. This value b squared minus 4ac greater than 0. So this equation is hyperbolic PDE. Let's see some of kind of this partial difference equation, parabolic partial difference equation, and b squared minus 4ac is equal 0. We examine heat conduction here with alpha as a coefficient. So we expect this is true that b squared minus 4ac is equal to 0. Okay, now we look at an example of one dimension. As one dimension PDE, one dimension, a spatial mesh, PDE. But we need to know what is the boundary condition of these problems. Before doing that, we discretize this one dimension mesh by finite number of internal nodes here. For a rod of length L, we divide this length into n+1 nodes. So we have step size here in one dimension, L on n. And what about time? The time is similarly broken into time step of size delta t. Now we use this expression to calculate x by I times delta x, and time is t equals g times delta t. J times delta t. Now let's see one of these method in parabolic PDE called explicit method. We approximate second derivative of t here, temperature, for example, related to variable x by a central difference. So if this is node I, it depends to another node here, node I+1 or and node I-1. The superscript here related to time. So here we half time evolution for calculating a second derivative here. This is j, and this is the same j, but the subscript is different, I+1 or I-1. But these heat conduction problems also incorporate with first partial derivative of temperature to time. So we need to approximate this partial derivative of t to times. So the superscript here I use. This is temporal nodes. In here we only drawing spatial node here, not temporal nodes. So we come to play this simulation, the construction of this simulation, and here is a coefficient alpha, and we come to an algebraic system, linear algebra. So we have to do many matrix operation here. Back to here, if you know the boundary values on the left, for example, and on the right here, on the right of the road, and you know how many internal nodes here, we can inspect here that we have 3 unknowns. Sorry for my bad writing. Unknowns, 3 variables. So we come to doing matrix operation. 3 times 3 matrix. Now, for short, this is how to solve the explicit method. For example, we have here a boundary condition on the left and on the right with step size, real step size here, 0.01 meter, and time step size 3 seconds. This is sum of parameters. And the initial temperature of the road is 20 Celsius degree. It means that, okay, here. It's all the same. They are the same. They are the same. So recalling that alpha here is the value of these fractions. We have here the value of alpha. Then we have the value of comparison of time dimension with spatial dimension here. Now, we plan to use a number time step here, 3 seconds. With this boundary condition, for all J here, which is index for time, boundaries, the temperature on the left always 100 degrees Celsius, and on the right always 25 degrees Celsius. This is the list of all temperature values at for all nodes, including interior nodes. So we here using this explicit relation between temperature at on every nodes, two adjacent spatial nodes here, by applying this boundary condition, setting I equal 0 here. We know this value. The next node I1 here, we calculate the value here, and the third, this is I equals 2. We have 20 degrees Celsius. For sure, this picture visualize the temperature variation at different location at different times. You will see that for a better performance, we have to use the smaller time step here, time step size here, 3 seconds. There is another method to compute the value of temperature at a specific node by time evolution using another node and another temporal node. Let's see this method here. We use the second derivative approximation here using central difference. And the first derivative of temperature to time here, we use backward difference scheme. At time level G plus 1. So if we substitute this approximation into this PDE, yields this relation, or if we rearrange this expression, we have this implicit method. Now, for the same example here, we use the same problems using the same time step size and step size delta x. for short, we come here to a matrix of problems. This is a matrix of size 4 times 4. Relatively pretty small matrix size, but this is a very simplified examples, and we have to look at the more efficient method to solve these matrix problems. So we have to use iterative methods, not using the traditional elimination methodology. Now, we have here many steps to solve these problems. The third method here for parabolic PDEs is the Crank-Nicolson method. I have to introduce this method because if you like to read many advanced book about numerical methods, this method very often was mentioned. The idea behind this method is how to similarize the accuracy of two terms here. The second derivative of temperature here, for example, and the first derivative of temperature to time here. The idea behind this approximation is next approximation of this second derivative. If you know trapezoidal rule to integrate the function numerically, you can remember these methods come from. Or in another word, this is averaging the value of two approximation of second derivative of temperature T here. Take the second derivative at time G plus 1 here, and at time G here. And we are doing, we are averaging this two value here divided by 2. This is the value at the midpoint of time step. That's why it is related to this first derivative of temperature. As usual, we can use this first derivative using 4 divided difference here, for example. So in this Crank-Nicholson method, we use the same order of accuracy. This is a visualization of the same problems here using a Crank-Nicholson method. And to sum up of these three methods, compare with analytical solution, you can see here these value compared to analytical solution. So Crank-Nicholson method is important to learn here. The second of partial difference equation form here is elliptic. I'd like to speed this explanation here. An example is Laplace equation governing by the temperature here. And we see a two-dimensional mesh. Now you know that this is a structure mesh. You could see here that the second derivative of temperature compute here related to adjacent nodes on the right here and on the left. And for the second derivative of temperature to y, using this nodes in y direction. One is at the top, one is at the bottom of this node I, j. J here is for y direction. And I here for x. What we are doing here, this is discretization using homogeneous structure mesh. And if we rearrange this approximation, we come to another algebraic system here. For solving this PDE, elliptic PDE for Laplace equation, we can examine the method here, direct method or Gauss-Seidel method or Lieberman method. I would like to skip this direct method. So I only show this slide here related to direct methods. But in principle, we come here to a number of internal nodes. If we calculate this internal node, we have 12 internal nodes. So we have 12 linear equations system. We have to solve matrix with size 12 to 12. This is what I mentioned before. Now, I think you have learned this method in elementary numerical methods for solving big matrix and iterative approach to solve big matrix, big size. So we can rearrange this discretization equation. That's the same description of direct method. We are dealing with 12 internal nodes here, or 12 unknowns. So for doing this iterative method, we supply the initial values, some initial values here for the unknown value of internal nodes. For example, here T 2.1 here, we don't know this value, so we supply this by 0. Another is T12 here. So we have T11 here. Just after we have this value T11 here, we use this value to substitute the value of T11 in another calculation right after this value is obtained. This is all values of internal nodes, including the boundary condition after the first iteration. Some of this is the temperature distribution using Gauss-Seidel method. Another method is Lieberman method. I intended to introduce this method as an advanced method, because the idea of this method is how to accelerate the process. This is one of the important key in doing computer operation, in doing calculation, in doing computation. For doing this Lieberman method, we use the concept of relaxation. Once you have one value of the internal node, we keep this value and we calculate another new value, and we're using the relaxation with a value of lambda here. So we have here another new or a relaxed value of t. Let's see this method. I think I still have time. 5 minutes.
Yeah, 5 minutes before break.
Okay.
Do you want to continue, or we can give a question session for the participants?
Okay. I will stop here. Please, if you have a question.
Okay, dear participant, do you have any question before we go to the break session and then continue again after that? Any question? If you have question, you can raise hand on Zoom. If not, I have a question, Dr. Irfan Hakim. So when we do discretization, is there any rule of thumb for the step size that we make, or the bin size of the discretization? Thank you.
Okay. Good point, Bu Lucky. How do you choose the value of delta t or delta x? We have to look at the real physical or astrophysical problems here. If we refer to Bodenheimer, there are three conditions to look at the choice of delta x. For example, here, first is mean free path. Mean free path need to very small compared to length scale, characteristic length scale of these problems. So this is one of rule of thumb for delta x. Another condition is interparticle force, for example, should short range. Yeah, we are dealing with force in astrophysical problems, and the in here we are in more details. Lambda need to be very small to related to local mean value of for example, very fundamental physical properties, local mean value, L mean value in scale LE for V, rho, or temperature, for example. The second one is shortening of force here. For this range, it was necessary to assure that is no interaction. No interaction. The third is about boundary condition. Diffusion, for example, need to be very small. So this is one of the rule of thumb for choice of delta X. For delta T, we need to assure that this is come to a stable computation. One of the condition is unconditionally stable. It was the ideal condition. Another is unconditionally unstable. Unconditionally stable means the errors decrease with time and ultimately vanish. For unconditionally conditionally stable, the error decrease with time, provided that the time step limited to be smaller than some critical value. And the value of delta T need to be approximate. For example, if we choose the delta X, we have this relation delta T to delta X on characteristic velocity. Characteristic velocity related to this length scale. Well, I hope this explains the choice of delta X and delta T.
Thank you very much, Dr. Irfan Hakim. So before we go to the break session, can we have photo session? So please, participant, can you open your camera? So we will have a photo session.
Okay. If all participants, please open your camera because we are going to take our picture. And for those who want to use video background, you can use the link in chat. Okay. Please open your camera. Okay, let's begin. For slide first. 1, 2, 3. Again, 1, 2, 3. The next slide. 1, 2, 3. Again, 1, 2, 3. And the third slide. 1, 2, 3. 1, 2, 3. Okay, thank you.
Thank you. So we will have break session now, and